Alright, so we got some questions, particularly about worksheet 128.4. Listen, this is incredibly tough stuff, to be honest with you guys. There's not really a formulaic approach. You've really got to be really creative and things like that. And honestly, I think what I'm going to do, I might actually just wipe this entire worksheet from the from sort of your assignments here. Listen, this is great stuff. It's high-level stuff. Is it real-world stuff you're going to have to really calculate? No, it's not. But anyway, I want to walk you through one of these at least. I want you to be able to see how it's done and sort of the thought process. Again, there's no tried and true way to approach these. It's going to change from problem to problem. But I want to look at number one here. So in this instance, they tell us the neutral has been removed from the neutral bar in the circuit. The current through the lamp, X, is what when the neutral is open. So how much current is flowing through that lamp right there? Again, we made a bad splice. We lost the neutral. So the moral of the story is if you lose a neutral, you essentially create a big, crazy combination circuit where all sorts of wacky stuff starts happening. So really, what I want you guys to know is why does that wacky stuff happen? And I think we'll look at this here. So what I've done is redrawn this circuit here over here, okay? So essentially we had sort of 2 lamps in the top bunch, 4 lamps in the bottom bunch connected in this way. I just redrew it, same circuit, but it kind of shows it a little better, I think, in my opinion. So, my first thought to you guys when you're working with combination circuits, try to break them down into more basic circuits. So if we look at this, within this box, we have a simple parallel circuit with 2 elements. In this box, we have a parallel circuit with 4 elements. Okay, so once you have that done, what I'd like to do is try to find the resistance of everything I can. Again, you're finding resistance. That's very important in any of these problems. But they tell us right off the bat, each lamp has a resistance of 80. Okay, so let's actually go ahead and do this. Let's solve for the resistance of this section and then the resistance of this section. And what we'll do is we'll kind of combine those values and think of this as one resistor and this as one resistor, where the total values, which we put in this table, the total values for this section actually represent the individual values if we were to combine them basically and redraw the circuit in this fashion. So now if we find the total values for this bunch and combine them, in your imagination, this is now its individual element with the total values from this bunch representing the values for this one singular element. And let's sort of run through that. I'll show you what I mean. So let's just calculate the resistance for this section right here. We know the formula for resistance is kind of this big, long, crazy guy, and I have a little cheat sheet I've made up here. And honestly, I'm going to try to put this in a format that I can share with you guys as well, and post that somewhere. But for now, again, this is a time where we're a little stuck using the parallel resistance formula, but we can punch this in. This will actually cheat a little bit for us, but it'll help get the point across. So we have 2 elements, each with 80 ohms. You can see they do the big resistance calculation here, which is this, boils down to this, one more step to that, ultimately comes to 40. Okay, so what we'll do, and again, when we're done with this, it's going to boil down to a series circuit like this. So let's just throw in our values basically for these 2, assuming they're actually combined to one element. So let's call that load 1, right? So you basically figured this section's resistance now equals, what do we say? 40, okay? And if you run through the calculation, you'll see that. So the resistance of that one is 40, alright? Let's make it darker font so you can see it. Okay, so let's do the same thing now with this section. So now we have 4 elements with the resistance of 80 ohms. So punch it in my little cheat sheet to save the time and watch it be calculated. You're going to find out you get 20 ohms of resistance. So same thing. And we're now going to go ahead and punch that into our resistance column for sort of what we're calling load 2. Again, if we imagine we've combined all 4 of these into one element, and that represents the resistance of that one element. Okay, and as we said, these would now be connected in a simple series circuit. Okay, normally current will go here, back through the neutral. We lost that neutral, so you can just pretend like it's totally gone, right? We have no connection whatsoever. So in this case, we've just made a simple series circuit, haven't we? And can we figure out any other values at this point? Well, we can. And that's going to be total resistance, all right? Reason being, we know the formula for total resistance in a series circuit is R1 plus R2, right? It's just simple as that. We can add them up. Do we know any other information? And we do, actually. What are we feeding this circuit with? And if you check the problem, they actually tell us we're feeding it with 240 volts. So that's actually our total voltage, right? So now the good news is we sort of have two values in this column. So we can go ahead and find amps or watts. I'm going to suggest we find amps because, again, we know amps is equal in a series circuit. So we find this, it'll allow us to fill in this and this. So Ohm's law tells us we have volts and ohms, we need amps. So V divided by R is going to equal amps. So we'll say 240 divided by 60 equals 4. Again, what we like about that, we can carry this 4 across to these two because amps is equal everywhere in a series circuit. We know that, right? So now what we can go ahead and do, and this is sort of what our first intention has to be, is how much voltage is going to be applied to each of these sections, all right? Because again, it looks like this. So we're really saying how much voltage is applied to this and this, and how much is applied to these 4, right? But if we look at it this way again, we need to find the voltage applied here, voltage applied there. We can do that pretty simply here back in our table with some Ohm's law. So if we need volts, we have amps and ohms. We are going to say I times R equals V, right? So we'll go ahead here and say 4 times 40, right, for our first guy here, gives us 160. Right, same thing for the next bunch. We can do 4 times 20, gives us 80. Okay. So the important part of that process is we now know the voltage applied to each of these sections. So if we now come back here, we know that the voltage applied to this section is going to be the voltage applied if we rewrite it like this, which again we just found was 80. Okay. So now we know there's 80 volts applied to this section. So ultimately they want us to find the current flowing in lamp X. So let's just look at this section of a combination circuit by itself. Right, I'm sorry, a parallel circuit by itself. So what we can do is actually take the values from this column, because remember that this column represents the values here, okay, or I'm sorry, right here at this element. So we can take the values from this column, representing that element, and we can go ahead and place them in the total column of our new table. So we're going to do 80, we're going to do 4 and 20. We're going to actually set up a new table, a new calculation for just this section of parallel circuit. Again, we found these total values by solving the circuit in this fashion. So the values that represent this, which were this column here, now represent the total values for the circuit. So we can fill those right in. And again, we said we're solving for sort of this parallel circuit section here. So let's think back to our parallel circuit rules. Can we do anything? Do we know anything? We could find watts using Ohm's law. Doesn't really help us here, so we won't do that. However, we know that voltage is equal everywhere in a parallel circuit. So we can now enter and carry over this 80 volts to all 4 circuits. Okay. Another piece we know, and a piece that might be kind of easy to forget about, is we also know the rated or they've given us the ohms of these 4 resistors. So we already know that. They told us that. So that represents the ohms of element 1, element 2, element 3, and element 4, or lamp 1, 2, 3, 4, whatever you want to do. So at this point now we actually have 2 values in every column. We can use Ohm's law. And again, they were looking for X. These are all the same, so it doesn't really matter, but technically X is our load number 2 here. So let's use Ohm's law to solve for amps if we know volts and ohms. So quite simply here, right, it's V divided by R, or in this case, 1 divided by 1. Or, I'm sorry, 80 divided by 80 actually gives you, guess what, 1. Okay, so that's your answer. That was a long process. And again, the best thing I can tell you, simplify the circuit. Look at this section as a combination, this section as a combination. Solve for these values as best you can, starting with resistance. Solve for these values, starting with resistance. Then find your resistance of the circuit as a whole. So again, we now sort of rewrite it and imagine it like this. find the resistance of the entire circuit, and once this is simplified, you can then sort of apply those rules that we already know for solving series and parallel. Once you find the value you need, then when we're back looking at it this way, in this case, we need to know how much voltage was applied to this section. That was the only way we could do that. So, I mean, you can see it's a lot of back and forth, kind of combining things and looking at the series and parallel circuits as they combine and change. Again, this is literally as tough as it gets. This is a very difficult section, and quite frankly, upon reviewing this, I'm going to actually pull that from your required assignments here. I do want you guys to sort of look at this, think about it, at least understand the brief idea. So you know, if you ever hear a service call where half the lights are really bright, half of them are burned out, some are not working, usually it's a bad neutral, and this is why. Okay, so understand that much. I'd love if you could really solve one of these. Frankly, it's very tough stuff. You're not going to see it on the final exam. It's not something you're going to do in real life. For me, it's more of a curiosity of understanding what's going on. So again, please don't sweat this stuff. I'm actually going to pull this particular assignment, 128.4, out of your assigned work. But again, take some time, watch this video, think about it, and catch you on the next one.